Hello, my name is Sam, and today I'm going to try and simplify down a really important part of electrical engineering, the capacitor, and specifically what happens when you apply DC voltage to it. Simply put, a capacitor is a two-terminal device used to store electric charge in the form of an electric field. The capacitor consists of a pair of conductors separated a small distance by an insulator. A material, referred to as a dielectric, is inserted to increase the charge on the plates. Now, when you apply a DC voltage to a series resistor and capacitor, electrons are drawn from the upper plate to the positive terminal of the battery. At the same rate, electrons are being repelled by the negative terminal to the bottom plate. As a result of this, the two plates will have an equal but opposite net charge, the top being positive and the bottom plate negative. This potential difference establishes an electric field between the plates. A capacitor's storage capacity, or capacitance, is determined by the charge on the plate divided by the applied voltage and is measured in farads. In a DC network, the capacitor can undergo three phases, known as the charging phase, the steady state, and the discharging phase. These are the formulas for voltage and current during the charging phase, or the transient period. In these formulas and the ones to follow, the Greek letter tau, known as the time constant, is defined as the series resistor times the capacitance, measured in seconds. As can be seen from the voltage versus time plot, the rate of change, or gradient, is higher within the first time constant and much less within the fifth time constant. The rate of change is the same for current, however it now has a negative gradient. After 5 time constants, we can essentially say that the voltage is equal to the applied voltage and the current is 0. Thus, we enter another phase, the steady state. In the steady state, with no current flowing, we can theoretically replace the capacitor by an open circuit equivalent. The discharge phase occurs when the DC power source is removed, and thus the capacitor has the highest potential difference. The voltage and current across the capacitor at any time during this phase can be calculated by these formulas. Note the voltage across the capacitor does not reverse polarity, but the current reverses direction, hence the negative sign. We will do an example question, but in the interest of time, I suggest you pause the video to better see the working out. Part 1. To find the mathematical expressions for the charging phase, we must find the network's time constant. Subbing in our values for the network resistance and capacitance, we determine one time constant to be equal to 32 milliseconds. We can then write down our formulas for the charging phase and sub in the corresponding values. For part 2, we can recognize that if t equals 2 tau, the exponential component will simplify to e to the negative 2. Plug this into your calculator and you'll find the voltage value to be approximately 35 volts. Finally, for part 3, if the steady state has been reached, we can simply use our equation for capacitance shown earlier. Rearranging C equals Q on V and plugging in our values, we would deduce that there is